How do you stand Flippin science, looking at the effects on a species of low genetic diversity? Thanks to Sam Moyle for producing this PowerPoint. So science understands we're going to look at species or populations that have a reduced genetic diversity, have a higher risk of extinction, give examples of species with low genetic diversity. We've talked about some of these little bits and pieces here before. So species that only have a small genetic diversity within the population, perhaps because they've just survived a catastrophe, may not have the full diversity of alleles present from the original population. So that means the gene pool may have shrunk. That's due to a loss of the individuals present. If a small number of individuals from a population begin a new population, they may have far less genetic diversity than the original population. So you have a small mating population, and this is known as the founder effect. So here's a picture showing the difference between the bottleneck and the founder effect. So the bottleneck effect, I've used this picture before. So we have our original population, we go through some kind of catastrophe where few individuals survive. The surviving population might not necessarily have an exact mix of the original population's genes present in the gene pool, so we get a change in the presence of genes in the gene pool due to their big catastrophe leading to a smaller surviving population. With the founder effect, it's a little bit different. We can talk about in terms of, from our original population, a small number of individuals from that small population may be migrating somewhere, finding somewhere new. And they'll have a mix of genes present within them. Due to the different selection pressures present, maybe different genes present from this small gene pool will be selected for, and that will lead to a completely different set of genes present in the gene pool from these founders. In both cases, we have a smaller gene pool present, both in the bottleneck effect and in the founder effect. So let's look at some example species. So we've got cheetah, bison, and Tasmanian devils. So let's talk about the cheetah. So about 12,000 years ago, there was a mass extinction event that occurred that wiped out large numbers of the world's large mammals, and it included the cheetah. So the cheetah's numbers decreased significantly, and the genetic diversity decreased due to the bottleneck effect that we just talked about. Cheetah used to have a large habitat, the remaining cheetah I should say, but due to human activity that's significantly decreased. So there's about 7,000 cheetahs left in the world, and the largest population, so a big group in one area, is 1,500 individuals. These 1,500 individuals are geographically isolated, and there's no gene flow between those 1,500 individuals and the other cheetahs present. So there's a lot of inbreeding. Inbreeding leads to inbreeding depression, where deleterious alleles are more likely to pop up in the population. So you get more recessive characteristics popping up, and these can be not good for the organism. So genetic defects like dental anomalies and low sperm quality, these lead to preventing hunting and reproduction. If you can't eat your food, then you're not going to survive very well, and if your sperm quality isn't good, you're not going to be passing on your genes to the next generation. Let's talk about European bison. So in the early 16th century, there were 100,000 European bison present, and then it went down to 12 individuals in the early 20th century. Today there's about 4,000 to 5,000 individuals, but they are all descended from only 7 individuals. So there's a ridiculously low amount of genetic diversity present in the remaining European bison. There's very little for natural selection to work on because there's not much difference between the individuals because they're all very genetically identical. And again, we're going to get inbreeding depression occurring, so there's going to be harmful mutations that are likely to be widespread. And it's very hard to get any new beneficial alleles popping up because you're relying on mutation to produce that rather than what you get from sexual reproduction. So let's talk about the Tasmanian devil. So it was widely distributed all over Tasmania and also part of the mainland, the south of the mainland. About 12,000 years ago, there was low sea levels back then due to big ice caps, so that meant that Tasmania was attached to Australia still. There was a land bridge. By approximately 400 years ago, Tasmanian devils were no longer found on the mainland, probably due to competition and predation with dingoes. 3-1. After European invasion, the numbers were depleted due to hunting and eradication by humans. It was a case of, they will kill our sheep, let's kill them first kind of thing. And that greatly reduced the genetic diversity because we had fewer individuals being present. So all Tasmanian devils are very similar genetically. So their gene pool is very limited. This is particularly concerning because there's this facial tumour disease that started appearing in the late 90s, early 2000s. It's very fatal and prevalent in the remaining individuals of the species. Tasmanian devils fight a lot, and a bite from one of the cancerous devils to another transfers cancer cells to the face of the other devil. The immune system doesn't recognise the cancerous cells. Because the Tasmanian devils are so closely related, it doesn't recognise them as even foreign cells, so they're not getting attacked by the immune system. That's due to their very limited genetic diversity. So here's a healthy Tasmanian devil, here's an unhealthy Tasmanian devil without facial tumour. Zoos across Australia went into rescue mode for the Tasmanian devils when the facial tumour disease emerged. So populations on the mainland that had been sent to zoos and wildlife parks were used as breeding populations to help restock Tasmania's Tasmanian devil population. So without these kind of interventions, it's probably likely that the Tasmanian devil would go extinct. Even with these interventions, the future for species like the Tasmanian devil, which have a very limited gene pool, aren't great. If you don't have a huge diversity in the genes present in the gene pool, and there's a change in the environment, like something like a facial tumour popping up, you don't have a lot of variation for natural selection to act upon to result in your species surviving. So if you don't have much genetic diversity, it's not good for you as a species, and extinction is much more likely. So let's do our check. So species or populations that have reduced genetic diversity have a high risk of extinction, and give examples of species with low genetic diversity. So now in Flippin Science, we looked at the effects on a species of having low genetic diversity. That's it for Flippin Science today. See ya.